A NAS appliance, often called a NAS array or a file, is a form of storage array, and we cover the common architectures of NAS arrays in the lesson on storage arrays, but we'll still cover off the basics in this lesson. A NAS array is a computer system, but it's one that's built specifically to deliver NAS storage over TCP/IP networks. So, it has its own hardware, CPUs, memory, network ports, hard drives, the lot. It also runs specialized software, often a fork of the Linux kernel, but the point is, it's highly tuned and highly customized for performing NAS-related functions. As such, the software is much simpler and much more specialized than the software on a general-purpose file server, such as a full-blown Windows server or a full-blown Linux server. It cuts out all of the fluff that you get in general-purpose operating systems. This leads to fewer bugs and fewer security patches due to the smaller attack surface of the smaller, hardened and customized operating system. So all in all, they deliver simplified management, improved performance, improved availability and hardened security. So let's talk a little bit now about NAS Performance and Features. NAS arrays usually provide better file serving performance than a general purpose operating system that's just been configured to act as a file server. We mentioned on the previous slide that this is in part due to their customized NAS operating system that's finely tuned to deliver file sharing services and cuts out a lot of the bloat that exists in general purpose operating systems like Windows and Linux. However, it's also often down to the dedicated hardware and specialized architectures that utilize things like large DRAM caches, utilize flash as a cache, and leverage large pools of drives. But another major factor in NAS performance is the network. If your network sucks, then you're in for a world of hurt when it comes to NAS performance, and probably also for NAS availability. And latency is the big killer when it comes to NAS performance. And by latency, we mean that anything that causes delay on the network. This includes common things such as time taken to perform the serialize and deserialize operations, routing decisions, store and forward queuing, packet drops and retransmits. The list could go on. The point being, low latency means relatively little network-induced delay and results in a high performance and good user and application experience, whereas high latency equals long delays and a poor user or application experience. We sometimes express latency as round-trip time or RTT. With round-trip time, this includes the latency incurred sending as well as receiving. And on this topic, a fairly simple point to note is that as packets cross more switches and more routers, the latency starts to increase. And that's because each switch and each router has to process and forward the packet, each time incurring additional latency. Now, traditionally speaking, Ethernet networks have been high latency compared to fiber channel networks, partly due to the way they store and forward frames rather than using cut-through methods. However, low latency Ethernet networking technologies are available, and if you require high performance, low latency network, then you should invest in the appropriate switching technologies, though these usually push costs in the wrong direction. Alternatively, of course, you could consider either direct attached storage or fiber channel SAN, as these are both very low latency. Another network-related performance factor to consider is TCP window scaling. TCP window scaling alters the size of the TCP receive window to allow for more unacknowledged data to be buffered. Think of it this way. Assume that a host advertises its TCP window size as 64K. Any host sending data to that system will know that it can send a maximum of 64K of unacknowledged data. As soon as it's sent 64K and hasn't yet received an acknowledgement, it has to stop transmitting and wait for that acknowledgement. If the host then increases the TCP window size to, let's say, 128K, then suddenly the host can send 128K of unacknowledged data before it has to wait for an acknowledgement. Now then, while TCP window scaling is far more prevalent and far more useful in high latency, low bandwidth environments such as WANs, It can still be useful on some local area networks, but don't make changes to this without either consulting your networking gurus or by being a networking guru yourself, as this can be a tricky thing to implement and to balance. On to another topic then. Jumbo frames is another networking voodoo trick you can have up your sleeve. Normally, TCP frames are 1500 bytes in size, but by turning on jumbo frames in your network can allow TCP frames to be as large as 9000 bytes. Now this can improve network performance by allowing the same dataset to be sent between a client and a server using fewer frames. But be sure to make the appropriate configuration changes on all of your network switches involved in the transportation of NAS traffic. Oh, and make the changes on your network interface cards in your hosts as well. And while on the topic of jumbo frames, the SNIA defines baby jumbo frames as a frame that's 2500 bytes in size, and these are utilized in fiber channel over Ethernet environments, where fiber channel frames, which are just over 2000 bytes, are encapsulated within baby jumbo Ethernet frames. And finally, on the networking front are technologies like NIC teaming and link aggregation protocols. Link aggregation technologies can improve network performance as well as network availability. They do this by bonding multiple physical links into a single logical link, with potentially the combined bandwidth of each of the physical links, and the improved link redundancy. For example, if one of the physical links fails, data can continue being transmitted over the surviving physical links in the bonded channel. And on the features front, NAS arrays and appliances often support advanced features and functionality such as snapshots, clones, replication, deduplication, compression, and a bunch more. But one area that traditional NAS arrays have struggled in is manageability. Large NAS environments can have tens or hundreds of NAS arrays, each individually managed, monitored, upgraded, you name it, and having hundreds of them to manage like this can be a nightmare. So, one technology that goes some way to resolving this is scale-out NAS.